Hello all, and welcome to this video where we look at how to graph the most basic form of a cubic function. Now really quickly, this is what the graph of the most basic form of cubic will look like. Y equals x cubed. Okay. Now why does it look like this? Well, let's think of a quadratic. Y equals x squared. We know that looks like this. Yeah, okay. And part of that is, if we think about input versus output, okay, we have x, we have input and output. Okay. What happens if we put in a positive x value? Well, we put in positive x and square it, we get an output of a positive. If we put in a negative x value, okay, and square a negative, that gives us a positive. Okay, and this is why we get this sort of U shape. Yeah, it doesn't matter what sort of x value we're putting in the most basic form. Okay, it turns our output positive. Now, if we think of the cubic, okay, just like we've got here, if we do our input and output again for y equals x cubed, okay, what happens if we put a positive in? Well, if we cube a positive, we get an output as positive, and that'll make it bigger and bigger. So get that sort of shape. Now, what if we put in a negative though? What if we cube a negative? Well, if we cube a negative, the thing that is new here, our output will be negative. Okay, so we put in a little negative, we get a little negative output. If we start to increase the negative input, cubing that, okay, we get that shape. And hence we have the standard shape of a cubic. Now, important points on a cubic is this point right here. Okay, this point where it changes. Okay, it technically comes up, and just at that point, it is right at that instantaneous point, it is flat. Okay. That point there is called the point of inflection. Point of inflection, because it changes direction, and we use POI for short. Okay, so that's the most basic form. Okay, so what is handy as you look up here, okay, the basic form of a cubic is f of x equals a, then x minus h all cubed plus k. That a, h, and k should look really familiar because we've looked at linear, quadratic, hyperbolas, truncus, circles, square root graphs, okay, and now we're having these same terms in a cubic. So if we go to Desmos really quickly, okay, we can have a look at the impact of that. So I've got this function y equals a, x minus h all cubed plus k. You should be thinking from the previous work, if we're writing it like this and we're using these variables a, h, and k, we've set a standard for what they are. We call a our dilation factor, h our horizontal translation, and k our vertical translation. So let's play with the translations first because they're most straightforward. At the moment I have h and k equals 0. So let's move h positive. As I make h positive, it moves our graph to the right. It translates our graph right. And if I make h1, my point of inflection is now at x equals 1. Okay, so it's a direct correlation. Make h1, my graph moves 1 to the right. And same if I now move it negative, it's moving the graph to the left. Okay, so h is our translation factor. K is our vertical translation. Same thing. If I make k positive, my graph moves up. So if I make k 2, 1, my point of inflection has moved to 2, 1. If I move it down, okay, same thing. If I make k negative, make it say negative 3, my point of inflection is at y equals negative 3. And I can use these together just like in the other graph. So let's make k equal to 2 and h equal to negative 1. And my point of inflection, sort of just like our turning point in the quadratic, my point of inflection is x equals -1, y equals 2, right there. And then if I play with my dilation, is just stretching it. Okay, so if I have a value less than 1 is our standard. If I make it less, it flattens it out as we get down to 0. But I won't make it 0 because of 0, well, that just deletes the whole function. And then as I make it greater than 1, it steepens up function. Okay. Then we should be thinking, okay, well, what happens if I make a negative? What if I make the function negative? Well, it flips, just like a quadratic. It flips. It reflects around its point of inflection. Okay, so we get that going on. So that's a quick look at the basic form of a cubic. We've seen a, h, and k before. We should be used to using them. So let's have a go at using them. This graph just talks about what I've just shown. This slide, sorry, talks about what I've just shown on the graph. Okay. Dilation reflection, so it reflects if a is less than 0. H is our x translation, k is our y translation. And our point of inflection is always at hk. So how do we use this to graph? Okay. The technique for graphing cubics of this form, okay, we're dealing with this form, we're going to deal with another form in another section, okay, but the first thing we do is point of inflection. Then we get our intercepts as our point of references to help expand our graph. So sketch the graph of fx equals x plus 2 all cubed plus 1. Okay, so from this we can say a is equal to 1, h is equal to, now the big thing here is that our standard form is x minus h all squared, all cubed. Okay, so if this is plus, technically that means our h value is -2 and our k is 1. Therefore we can say our p or I, our point of inflection, exists at -2, 1. So let's sketch that. So it's at -2, +1, so right there. Okay. So I'm just going to draw a little horizontal line through my point of inflection. POI, and that is -2, 1. Okay. Now I know, and I'll do it, oh, this is going to be hard because the eraser doesn't quite work on this. It's going to look something like that. Okay. The graph is going to look something like that. How we know how much it bends or how steep, how compressed or stretched or dilated it is, well, we have our a equals 1, but the best way to graph it is to, as it says, find our x-intercepts. So find our x, find x int, we let y equal 0. Okay, so we get 0 equals x plus 2 all cubed plus 1. So we get -1 equals x plus 2 all cubed. And here's something new. Can we take the cube root of a negative? Yes, we can. And we can take the cube root of a negative equals x plus 2. And the cube root of -1 is just -1 because -1 times -1 times -1 gives us our -1. So -1 equals x plus 2. So x is equal to -3. Okay, so that is our x-intercept. So it happens to be right there, -3, 0. Okay, for color. Just going to use color here to highlight the different points. Okay. So to find our y-int, as usual, we let x equals 0. So we get y is equal to 0 plus 2, all cubed plus 1 is equal to 0 plus 2 cubed is 8 plus 1 is equal to 9. Okay. And now here I have an actual issue with my scale. I've had -2, 1 is there, 1, 2, 3, 4, 5, 6, 7, 8, 9 is way up here. Okay, it's way up there. 0, 9. Okay, So now I can sketch my graph. Comes down there through like that. Need to put our arrows on the end. Label our axes. That's our x-axis. That's our y-axis. And our graph of f of x. Done. Okay, so that's how to sketch point of inflection. So think of working with quadratics. We found our turning point, then our intercepts. This is very similar. We're finding our point of inflection, then we find our intercepts. So nice easy question. Gets a little bit harder. What if we take the inverse? Okay, so we looked at inverses in functions, and when we take the inverse always reflects, okay, it reflects about the y equals x line. Okay, so you can imagine taking our blue line and flipping it. If you can see in the camera, we're flipping it about that y equals x. So this point here, flip it about the line so it comes out to there. Same here, take this point here, flip it about the line. Okay, if we're down here, this point here, move it towards the line, flip the opposite direction. Okay, we're just flipping. When we inverse, we can think about we're just flipping it about the y equals x line. So we can do that. We could graph the original function. Okay, so as we've got here, f of x equals x cubed, therefore the inverse, f of y equals y 1/3, or we could call it g of x equals x to 1/3 if we want to graph it on the same axis with x and y. And we could graph the original, graph in y equals x and flip it, or we can still use the same process of a, h, and k, graph the point of inflection, graph the intercepts, and we know what it looks like. So from this one, y equals x minus 1 to 1/3 minus 2. Okay. We see the 3, we just need to think that we're dealing with a cubic. Since it's 1/3, it's an inverse function. Okay, it's an invert. We could think of it as an inverse cubic. Okay, so a is equal to 1. It's the 1 out the front. H is equal to 1. K is equal to -2. Therefore, our point of inflection is at 1, -2. Now, I'm not going to put the dot in straight away, so I can find my x-intercepts first to see if that I need to adjust my scale so I don't make the same mistake as I made on the previous graph. So, x-int, let y equal 0. So, we get 0 equals x minus 1 to 1/3 minus 2. So we get 2 is equal to x minus 1 to 1/3. So the opposite of the 1/3 is effectively saying cube root. So the opposite of that is cubing. So we get 8 equals x minus 1. So x is equal to 9. 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to say that's 2, 4, 6, 8, 10, just so I can fit it on my scale. Take 2, take 4. X, Y axis. So that was my x-intercept. Now I'm going to find my y-intercept by letting x equal 0. So we get y is equal to 0 minus 1 cube root minus 2. So y is equal to -1 cube root minus 2. We get y is equal to, the cube root of -1 is -1 minus 2 is equal to -3. I'm going to use the same scale. -2, -4, 2, 4. Okay, so now I have my 3 points. Let's graph them in. So my point of inflection 1, -2. So right about there. X-intercept is 9, which is there. and y-intercept is -3, which is there. Okay, so we had 9, 0. We had 2, and over here we have 0, 3. Okay, I have those points now. I can graph it. So quickly, in a regular cubic, x cubed, point of inflection is horizontal. For 1/3, our point of inflection is vertical. So a little vertical line through, point of inflection that goes on like that, and then up through. That's f of x. Make my dot bigger to hide my messy line, point of inflection, and other intercept. There we go. Okay, that's graphing a inverse cubic. That's it. The really short section, really short video, because all principles are exactly the same as quadratics, hyperbolas, truncus, square root graphs, circles, and linear. We've worked the same way. Horizontal translation, vertical translation, dilation, and key point. It's exactly the same, just the shape looks a little bit different. Play around with Desmos if you need to practice. Any questions, stick them on the Edmodo page.